Good morning, everyone. Hope you had a great fall break. Welcome back to class. So we are going to pick back up in chapter 6. So we're talking about properties of the, or trying to get towards properties of the electron in a atom. We kind of started the chapter with discussion of light. So Wednesday's lecture was talking about the wave properties of light, so that we can understand then also getting into the wave-particle duality of light. So through the photoelectric effect, we were seeing light was behaving also as a particle. And so light was able to hit a metal and cause electrons to be ejected from the metal, but provided that the light had enough energy, and it's sort of on a single atom, how much energy it takes an atom to ionize, that each photon of light had to have at least that much energy in order to cause an electron to be ejected from the metal. And it actually led to the idea that light can be described as containing a certain number of photons, where one photon is the least amount of light that you could possibly have, is just an individual wave of light. And then having multiple photons would be having a more intense wave, or having a more of those waves that could be traveling towards our atom. And that the wavelength is so we can describe the light's wavelength cycle by how long the wavelength is. Really long wavelengths, radio frequency, very low energy form of light. So long wavelength, low energy. Then short wavelength would be like gamma ray, X-rays, really high energy now, because we have a very short wavelength, very high frequency. So you might remember that energy is equal to Planck's constant times the frequency. So high frequency, high energy. So light of a minimum frequency is needed to cause electrons to be ejected from a metal surface. And so we want to go to a high frequency, high energy, and that would be a low wavelength. And so wavelength's inversely proportional. We might remember two equations from last time, or these equations here. E is equal to h nu, and then also equal to hc over lambda. So as we go to higher frequency or lower wavelength, we're going to a greater energy, and that's the energy for a single photon. And so where we'd like to go from this is if we kind of start the chapter with the wave properties of light, and then some of the particle properties of light behaving like a particle coming from the photoelectric effect, then let's talk about the electron itself in terms of its properties. We know the electron is a particle, so it should have a particle behavior, but it's also a very light particle that we're going to see is traveling very fast. It's also going to therefore have a wave property as well. So we're going to see the electron has a wave-particle duality about it as well. And so our starting point into this here in the mid part of the chapter is to sort of start by looking at a light source, taking just an ordinary, like a flashlight, passing a portion of the light through just a slit, so you can take a portion of the light that you can then direct towards a prism. And so then this little narrow portion of light, we can then separate it into its different wavelengths through a prism. And then through a prism, we can see that we get a spectrum emerging where we kind of have all of the colors present. So we get a broadband spectrum for a light source, like a light bulb in the room, or an incandescent light bulb like a tungsten filament, an older style light bulb, or just like a flashlight bulb. We would see a broadband spectrum. Now at the time, it wasn't really clear why this would be the case, but now the explanation could be, and something we can maybe understand at this moment, would be that the energy in the batteries of the light bulb, or if we have this plugged into the wall, the high voltage energy that we're giving to the light bulb to heat it up, to cause it to appear bright, is allowing the metal, or whatever the atoms are in the light source, to go to some hot state. And then that hot state is then coalescing back down to some sort of cold state, or some lower energy state. So we're taking high voltage energy to create the atoms into these like hot, highly energized states, and then it's the transition of those states down towards a cool state that allows that energy difference to give off the energy equal to a photon of light. So you can imagine this kind of happens on an atom-to-atom basis, that a single atom of tungsten or whatever the metal is, and say the light bulb wire, absorbs the high voltage energy, goes to some high energy state, and then it coalesces back down to a ground state, and that energy difference is used to create a photon of light. And so one atom having an energy transition, creating a single photon of light, and then you can have a variety of states. So if you're thinking, well, how many different energy states are there? What if you have all these different energy states here? What if in your cold state you have all these energy states, and then you have all these different transitions that are possible? And so you have all these different transitions that are kind of giving us this broadband spectrum of light. So we're seeing photons, or an absorption spectrum showing us multiple different wavelengths of light appearing in that light source due to all of those different states that are existing within usually a larger atom here being the light source, like a tungsten filament or some sort of gas mixture. And so if we then go to a simpler light source, if we go to a hydrogen tube, so we have a tube just filled up with hydrogen gas. So this tube here just has H2 gas in it. And then we pass a voltage either end. So we have just a voltage going through that gas sample so that we can take that H2 sample and give the hydrogen molecule energy for it to do something with the energy so it can absorb the energy. We give it so much energy through high voltage energy that we can break the H2 bond and then create like what we would think of as being like hot atoms of hydrogen. And so in the process here, we're creating hydrogen that's in these excited states. So you can think of hydrogen here being in some sort of excited state and then coalescing back down towards low energy states of hydrogen here. And so if you can imagine there being these different transitions taking place within hydrogen, hydrogen being a small atom, having just one electron per one H atom, then is going to allow there to be some more distinct transitions that take place. So instead of seeing a broadband spectrum, when we take a slit of this light, pass it through a prism, so instead of seeing a broadband spectrum, we see 4 distinct transitions. If I zoom in a little bit, you might see them on the screen. I don't know how well the projector screen shows them, but in your notes, you can probably see there's a transition here, 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 and here. So instead of a broadband spectrum, we see very distinct, like almost lines. We call this like a line spectrum, where we're seeing just 4 distinct absorbances, or not absorbances, emissions here within the spectrum. So what we're seeing is we're taking the hydrogen sample, passing high voltage through it. It's giving us a light, and we're looking at the light to see what we can see being emitted away from this light source. And so from the fact that we see emission, it's kind of telling us that we should have some sort of hot state and some sort of cold state, and then just an emission from the hot state down to a colder state. And so the same basic process is happening for hydrogen as it was for the previous slide, except now with a simple one electron atom, we can see more distinct transitions taking place. And so I'm just calling this H star to kind of have that be like an excited hydrogen atom and coalescing back down to maybe what we would think of as being like a ground state hydrogen, towards the lower energy states possible for the H atom. And so the distinct transitions, these are not worth memorizing, but there's 4 transitions around 410, 434, 486, and 656 nanometers. These are the only 4 lines in the visible spectrum for hydrogen. We'll see a little bit later that there's UV transitions that are possible. So if we looked in the ultraviolet region, if we had the ability to see those transitions, we would see a few more. And if we could look in the infrared region, if we had some sort of infrared viewer that we could see beyond the visible region, then we could see transitions in that region as well. And so the hydrogen emission spectrum is just showing us some distinct transitions, and specifically 4 of them in the visible region. So the question would be, well, what's causing these transitions to take place? What can we learn about those transitions? And then what from that process can we then apply to other atoms? Can we take anything we learn about hydrogen, apply it to larger atoms? And that will be, and we'll see how that kind of goes. So the 4 emission lines led people like Balmer to try to just come up with a formula to try to reproduce or calculate those numbers. And so Balmer was able to come up with what we would call like an empirical equation, just like an equation where you're just trying to like fit an equation to the data to reproduce those 4 lines in the spectrum. And he found that he could get an inverse of the wavelengths from those spectrums by taking a constant that was called the Rydberg constant, and then minus 1 over n1 squared minus 1 over n2 squared. And then n1 and n2 just had to be whole numbers. And so in this equation here, n1 had to be equal to 2, and then n2 had to be equal to 3, 4, 5, or 6. And again, not worth necessarily memorizing why this is or how this is. And in fact, I don't even really play around too much with this equation because it's kind of boring, but we could look up the numerical value of the Rydberg constant, and then we could do some math here and show that you could, with this equation, reproduce these transition values in the spectrum. We'll see a little bit later, we can do it with a slightly similar equation, but this equation doesn't really provide us with too much of the why these particular, it doesn't really tell us what the n's are even corresponding to. It's just really a basic equation that was found just by fitting the data to some sort of an equation. But the idea here that n1 being some whole number values, these n being some whole number values is telling us that this looks like a sort of quantized problem. This looks like an energy state problem, that n must be some sort of like quantum number where it has to be whole numbers and nothing in between. So it's relating to kind of that whole idea of being like having quantized energy levels. Even the idea of like an ionization energy from the photoelectric effect, that the ionization is taking some minimum energy is another idea of like quantized nature of matter, that it's not any energy, it's just a very specific amount of energy that's required for a certain transition to take place. So Niels Bohr is going to try to provide us more detail. So let's take a look at what we would call the Bohr model. So the Bohr model kind of then said, well, the energy of the hydrogen atom can actually be said to or be shown to equal minus the Planck's constant times the speed of light times that Rydberg constant, and then times z over n squared, where z is the nuclear charge. So z is equal to 1 for hydrogen, that's just the nuclear charge. In this equation, it's really probably not going to be something we do here to show this, but you can technically apply this to other one-electron systems of other atoms, which most of these are kind of not really interesting in any kind of chemical way, but you could apply this like the helium plus has 1 electron. You could apply this equation to lithium 2 plus, which has 1 electron. You could apply this to beryllium 3 plus, which has 1 electron. So all these here have 1 electron, and just their z values are changing. So the z for helium would be 2. The nuclear charge of helium is 2, 3 for lithium, 4 for beryllium. But again, it's like just kind of showing you could apply this equation here and just kind of modify your z value for those atoms and come up with some predictions for those atoms. But those are not the most commonly observed. In fact, lithium 2 plus is nothing we're ever going to encounter in any kind of compound. Same thing with beryllium 3 plus. Helium plus is kind of not something we're going to encounter either. So there's really not much educational value we're going to learn from those atoms. But this equation here is only going to work for 1 electron systems. We're going to find that it's not going to work for helium with 2 electrons. It's certainly not going to work for anything with 3 or more electrons. And so if you take H times C times the Rydberg constant, you get this number here, and it works out to be units of joules. And so the energy of the hydrogen atom is shown to be a function of that n value. And so then energy is minus 2.179 times 10 to the minus 18 joules times 1 over n squared, where n is this whole quantum number that has to be 1, 2, 3 on upward, can't be 0. The Bohr model actually does not give a really good reason why n has to be 1 and not 0, but it just doesn't work when n is 0. And so the best explanation the Bohr model gives is, well, if you throw n of 0 in, it just doesn't work. So there's no experimental observation of n being 0, and so the lowest n can be is 1. And so then if you were to plug in 1 for n, then this would be equal to minus 2.179 times 10 to the minus 18 joules, would be that product times 1 over 1 squared. And then if you were to go up to n equals 2, you're going up to minus 1/4 times hc, because you're now taking 1 divided by 2 squared. And so the energy it takes to go from n1 to n2 is a big difference of energy relative to the difference to go up to n equals 3. The n2 to n3 difference is now a little bit smaller than the n1 to n2 being bigger, because we're just going from 1 divided by 4 to 1 divided by 9 times hc. So the difference of energy here is not as great. If you keep going to 4, 5, 6, we're approaching 0. So we're approaching at infinity for n. The energy would be approaching 0 as n approaches infinity. So we're approaching an energy of 0 here for the atom. And so you could do things like calculate an ionization energy. This, I think, is on a later slide, mentions this, that if you remove the electron to go to H+, that's kind of what n equals infinity is kind of getting at, that this is what looks like H+. So the energy difference between hydrogen in its ground state and H+ is this difference here, which is equal to plus 2.179 times 10 to the minus 18 joules. And that's per one single H atom. That's why the energy is so small. So this is the energy for a single atom. And if we were to convert this to using Avogadro's number, just multiply by Avogadro's number to go to per mole, and then convert to kJs, this is equal to 1312 kJs per mole, which is the exact ionization energy of hydrogen. And so we get plus, let me rewrite this just to make sure that's clear, plus, and again, this number isn't worth memorizing, but plus 1312 kJs per mole from this equation is the exact ionization energy of hydrogen. So it takes 2.179 times 10 to the minus 18 joules to ionize each one of those H atoms. Okay, now from the photoelectric effect is the idea that if we wanted to go from N1 to N2, then the atom has to absorb energy. So if we want to go from a low state to a high state, the atom has to absorb energy. And then if we want to go from a high to a low state, then the atom can emit energy. So going this way, going up, is the absorption of energy, or the absorbance of maybe light to undergo that process. So if we want to go from N1 to N2, then we have to have the H atom absorb a photon of light exactly equal to that difference of energy. And if we want to go from N2 to N1, then the atom is going to emit energy, possibly in the form of a photon of light being given off equal to that difference of energy. And so then if we then go back to kind of the Balmer series, where it was finding that it was like one of the N values was 2 and the others were 3, 4, 5, and 6. And if we're seeing emission, that's coming downward. So what the Balmer series is suggesting is that we were seeing these specific transitions, 6 to 2, 5 to 2, 4 to 2, 3 to 2, that these are the transitions that we were seeing in the visible region. So those are the transitions leading to that visible spectrum that we are observing or showing you for the H atom. And, again, this is on a later slide, so I'm kind of talking about a lot of things that we'll summarize over a couple of slides. But if you imagine the same set of transitions all the way down to N1, you might be thinking, well, why would the transitions not go from those energy states all the way down to N equals 1? And the answer is they do. We can have the transitions take place where we go all the way down to N equals 1. Those are just really high energy transitions. So those transitions are in the ultraviolet region. So those would be UV transitions in the UV spectrum for H atom. And then if you look at these lower energy transitions, going down to 3 or going down to 4, those would be in the infrared region. And so those transitions do occur. So all these transitions are taking place. So our light sample absorbs heat. We create these highly energized atoms in this region here. Those highly energized atoms have to return back down to their ground state. Eventually we form back our lowest state, N equals 1. And then it'll recombine with another H atom, so the H2 molecule reforms, and we kind of just have this process of H atoms cycling through, some of them absorbing light, giving off light as they coalesce back towards their ground state, reforming H2 in the process. So if you imagine your light sample, we never really lose the H2 molecule. It's a sealed gas tube, so we just have like a recycling of these events as this light's being absorbed. So this question here is one I think we can show and have an understanding of how this is working. So if we wanted to try to show the wavelength that's emitted by the 6 to 2 transition by the H atom, we should be able to show that with the Bohr model equation on the page here. And the way I would think of doing this would be to calculate the delta E for this transition, and then from that delta, I love your guys like alarms. I'm sure your roommates do too. But it was actually funny. I was up at 4 a.m. today. My son's on his 8th grade trip, just left this morning for DC. I'm sure how many of you guys did like an 8th grade trip like that. And so we were up super early. My daughter's in 6th grade. She got up with us. And she had her phone. She went back to bed after we got back and dropped them off. Her phone had been going off for like an hour. I don't know why she had like all these alarms set, but her phone just keeps erupting with alarms like that. So anyways, so can we use the Bohr model to calculate and reproduce one of those transitions from the H atom emission spectrum, the 6 to 2 transition? Now, if you recall, the transitions were like 410, 434, 4 something, and 656. Which of those 4 do you think would be 6 to 2? Like from the 6 to 2, 5 to 2, 4 to 2, 3 to 2, which of those transitions do you think is the greater energy transition? 6 to 2, 5 to 2, 4 to 2, or 3 to 2? Probably the 6 to 2 is the greater energy transition. And then if you look at the visible spectrum, 656, that's the lower energy side because that's closer to the IR region. 400's closer to UV. So probably the 410 So I'm probably thinking this will be the 410 transition, is my suspicion here, because this should be the greater energy of those 4 transitions, but let's see if that works out to be the case. And so the way I would calculate this is to calculate my delta E for the H atom. So the idea is the H atom in n equals 6 has energy to lose. So going from 6 to 2, the atom should be losing energy, and this becomes kind of like a system surroundings problem. The energy lost by the atom can be gained by the photon that emits away from the gas tube. And so we should be taking our final state minus our initial state. So if we're going from 6 to 2, then 2 is our final state, 6 is the initial state. And I can do one of 2 things. Like, this is usually the given on a test, is this equation here. So on a test, I'm probably thinking, if this is the equation I have to use, I'm just plugging negative 2.179. A lot of times they round it to minus 2.18 times 10 to the minus 18 joules. But I'm taking that times 1 over 2 squared, and then subtracting that 1 over 6 squared. So I'm just going to plug into that equation. So I'm just going to plug into this equation here, take negative 2.18. I'll round it to 3 sig figs, that's fine. 18 joules. And I'm going to multiply that by 1 over 2 squared. I want to be a little careful with my minus signs here too, because I'm just taking the equation's negative 2.18 times 1 over the n value squared. So that's my E2. I'm going to erase this here to not get mixed in. Then I'm going to subtract negative 2.18 times 10 to the minus 18 joules times 1 over 6 squared. So in terms of my calculator, I'm probably going to do 2.18, make sure I do the negative. So negative 2.18 E minus 18 divided by 2 squared. So dividing that by 4. And then I just try to do the minus signs and not be too smart. I try just to do what's on my page. I do then minus and then negative 2.18 e to the minus 18 divided by 6 squared. So I work that out. I get negative 6.06 times 10 to the minus 19 joules. Now, negative to me makes sense because the atom is losing energy. The H atom loses energy in this process. Where does the energy go? The photon gains that energy that's lost by the H atom. So our photon energy, the energy given to the photon that's created by this transition, would be equal to plus 6.06 times 10 to the minus 19 joules. And then that photon energy is equal to hc over lambda. Just from E is equal to hc over lambda from photon energy. And so I should be able to solve for my lambda by taking hc divided by 6.06 times 10 to the minus 19 joules. I'm like debating if I need to show h going in. You may know h well enough to do this without writing this down or without me having to write it down, but it's 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. So the seconds are canceling, and then divide by the number of joules. So the joules cancel. So we're left with units of length being meters. getting a wrong number, so I'm double checking my math on the previous step. Okay, I think I miscalculated. Did anybody else do this calculation here? Put this in red. I think this should have been, I've just recalculated, it should be 4.84 times 10 to the minus 19 joules. So I don't know how I miscalculated that, but that doesn't seem to be the right number. So if you were to double check that step, and we put this right number in here, so let me fix this to that number, 4.84. Because this should come out dead on. Okay, that is looking better. Not sure how I screwed that up, but this works out to be 4.104 times 10 to the minus 7 meters. Just taking HC divided by that energy, and then converting to nanometers, multiplying by 10 to the 9. Is 410 nanometers. So reproducing that the 410 transition for the H atom is leading to the 410, the 62 transitions leading to the 410 nanometer photon in the H atom emission spectrum. Now we could go through the 5 to 2, 4 to 2, 3 to 2 and see that the 434 is the 5 to 2, the 486 is the 4 to 2, and the 656 is the 3 to 2. But the idea is that if you imagine we go 7 to 2. 7 to 2 is now going to be outside the 400 nanometer region. I think it's around 390 nanometers, so it's just into the ultraviolet region. So if you have 7 to 2, 8 to 2, those transitions could be taking place. They're just out of the visible region. And then we could have the transitions going all the way down to 1. If we wanted to calculate them, we could, but they're just in the ultraviolet region, just a really high difference of energy. And so now, one of the things you might be wondering is, well, why is it only possible for the H atom to transition from n equals 1 to n equals 2 to n equals 3 to n equals 4? Well, one of the explanations is it comes down to kind of like wave mechanics, and that if you think of having n equals 1, there's the idea that that would be like no nodes along like a point-to-point line. So if you imagine 2 points on a line, there'd be like no nodes or no passing through the nucleus. So it's for n equals 1, looks like this. If you have n equals 2, looks like this. Now imagine we're bending around the atom, and the atom has to have a wave motion around the atom where it's maintaining either 0, 1, or 2 nodes. Then around the atom, you have to have an integral number in order for all those wave cycles to kind of line up around the atom. And so it ends up being that you have to have a whole number for n, otherwise we're not getting a like wave cycle that replicates itself around the atom. And so we have to have a whole number in order for either the points on the string to kind of be able to have a trajectory backwards and forwards, and the same thing bending around the atom would need to have a whole number for n. So that's a brief explanation for the quantized nature. And also to have n equals 0, one explanation could be, well, you have to at least have, if n's 0, then what would that even mean? It's hard to imagine a meaning thinking of the wave nature of light to have no, like n equals 1 is already no nodes, so how can you have fewer than none? So that's maybe an explanation for why n equals 1 is the first n value as opposed to n equals 0. So what do these transitions mean again? So the idea is that from the Bohr model, we can see that the energy of the H atom is a function of its n value. To go up in n is to increase the energy level of the atom. To go down in n values to decrease the energy of the atom. And so to go up is requires the absorption of energy. So a positive delta E for the atom is the absorption of energy of photon is absorbed in this instance. So we can absorb a photon to go from a low N to a high N. So that would be absorbance to go upward. And then to go downward is a loss of energy for the atom, and then that energy being lost given to the photon. And so if the N drops, then we are losing energy, giving photons off. So from top down, emission of photons. From the bottom up, absorbance of photons. And by absorbance, we mean you can shine a light source in on the atoms, they'll absorb the light. And by emission, we mean that they'll give the light off, emit it away from the light source. Okay, so what else can we do here? Well, we can talk like relatively. So which wavelength below for the H atom causes the greatest wavelength of light to be emitted? And this question here is basically saying for these choices, which of these choices has the H atom undergoing the greatest possible emission of light? So think about this question for a minute. Feel free to compare answers with your neighbor. Does anybody feel confident in knowing the answer? Anybody? Nobody's confident. That's okay. Yeah. So I think that's a good choice there. And so A and C I think can be quickly ruled out because A and C go from low to high. Those require the absorbance of light, not the emission. So light has to be absorbed to go from the low to the high end. And so we can rule A and C out. If the question was asking which of the transitions could allow the greatest wavelength of light to be absorbed, then we're looking at choices A and C. And then in terms of the greatest wavelength, this is going to have the smallest energy. So the smallest change in energy is required to have have the greater wavelength. So have a greater wavelength, has a lower energy. This is coming from E of the photon, is hc over lambda. So as we go to a longer wavelength, we go to a lower energy of the photon. So the lower difference of energy between the H atom for its energy being lost is going to correspond to the greater wavelength, and that's the 4 to 3. So the 4 to 3 has a smaller difference of energy than the 3 to 2. Now, one of the takeaways from the Bohr model is that as you go from N1 to 2, big difference of energy, to 3, smaller difference, to 4, even smaller, to 5, even smaller, and then even smaller until we get up to N equals infinity. Now, something that when I was probably in this class that I didn't have a appreciation for, that I later gained an appreciation for through work I did in grad school, is that we would actually create H atoms in the N equals 40 to N equals 50 state. And it was actually possible for us to have the H atom in what we would call these high Rydberg states, where you could have the H atom with just enough energy holding that electron into place. So as you go from N1 to N2 to N3, we're really pushing the electron further away from the nucleus. And you can get up to about 40 or 50 or so, and that electron is still loosely attached to its nucleus. And then all you need is to put a little potential onto that atom, and the electron will fly off. And so we were actually able to detect H atoms in reactions that we were taking gases and molecular beams, colliding them together, and fragments were going towards a detector. and we would create the H atom fragments flying away from this reaction in these like high Rydberg states. And so you can go up to n equals 40 or 50 or so and actually have an actual atom that is somewhat stable enough to exist for that period of time for the atom to fly to a detector. I don't expect that you take much away from that other than the fact that the n value can go quite large, especially when you have a lot of energy that the H atom can absorb through like high voltage energy from the lamp source. You have these hot states coalescing down to these colder states, and then we can kind of see what's going on and fit it to these equations using the Bohr model. So the H atom is very unique. One electron system with one proton in the nucleus allows us to have a really good understanding of what's going on, and also allows us to see the energy levels are quantized, but then allows us to see the complexities. We even go to 2 electrons that this approach breaks down. As we go to 3 electrons, it definitely breaks down. That we need a different approach for multi-electron atoms. You probably know the approach. It's going to be orbitals, the idea of like 1s versus 2s versus 3s versus the 2p orbitals, the 3p orbitals. So the orbital nature of matter comes down to us then saying, well, why don't we start thinking of electrons as behaving with some sort of probability of where we expect to find them, instead of being a discrete particle that has a discrete wave being treated here like with the Bohr model. And there's actually elements of the Bohr model that do violate some other principles we'll learn, like the uncertainty principle is actually being violated by some aspects of the Bohr model. If we start to think of the radius, we can calculate an average radius of the atom with each n value, and that kind of suggests we might know where the electron is at any given moment, which turns out not to be the case, that we'll soon see. So a quick summary here would be that the H atom, we can have these transitions between the n equals 2 and greater down to 1. We call that the Lyman series. So the Lyman series are the set of transitions that go from some n value down to 1, or from 1 to some value. So n equals 1 to 2, 3, 4, 5, 6, etc. is the Lyman series, absorbance going up and emission coming down. The Balmer series is the 3 to 2 transition, so the emission spectrum n equals 3 or greater down to 2, that's our Balmer series. These are in the visible region, at least through n equals 6. And then these are in the UV region. All the way down to n equals 3 is in the Paschen series, that's in the IR region. And so a lower energy region of the spectrum, so you can see high energy down to 1, lower energy visible down to 2, even lower energy IR down to n equals 3. And then you could have transitions that stop at n equals 4 or n equals 5 that are even lower energy parts of the IR spectrum. And then if you go from n equals 1 to infinity, that's ionizing the atom. That you could show this, it's really not worth the calculation to show, but you could calculate the ionization energy in per mole like we did earlier, is that 1312 kJs per mole. The takeaway for me is that that's the right and correct and observed ionization energy of hydrogen. So we get a good agreement between the Bohr model and a property of hydrogen. So the Bohr model does have limitations. It doesn't quite describe why n equals 1, 2, 3, 4, although the wave explanation that we kind of ad hoc come up with, I think helps us understand why the n has to have whole numbers. It doesn't really help us understand multi-electron atoms. If we want to get past hydrogen, we have an issue here of getting this equation to work. And then it doesn't really describe the wave-like behavior, kind of violates the uncertainty principle. So we need to talk about other aspects that could be going on with electrons to get into our orbital description of matter. And so let's talk about the wave nature of matter. So de Broglie came up with an interesting approach, which kind of actually started from Einstein. It would be interesting if we could talk a little bit more about how Einstein measured and determined from a fit the Planck's constant. But one of the things that Einstein started with when he was relating wavelength to energy was that he was taking h over mc. This is for a photon. So this is like a key equation behind Einstein's work in the photoelectric effect, was this equation here. And so the idea of this equation then kind of led to, well, what if for a particle like an electron that has some mass and some velocity, what if we plug in to this equation and calculate the wavelength of matter as being a function of Planck's constant, the mass of the matter, and then times the velocity of the matter. And so for light, this kind of simplified down to the speed of light. We tend to say like photons have no resting mass. If you were to calculate from E is equal to mc squared, if a photon has energy from E is equal to mc squared, you'll see a photon that that's in motion does carry some mass associated with it, but that's how light's behaving like a particle. That's like part of the wave particle duality. But now for a particle that's not traveling anywhere near the speed of light, so when you have an electron, or even imagine like a baseball, baseballs are nowhere near the speed of light, but you can imagine they have some velocity, some mass, and we can calculate their wavelength in a similar approach. And so the question becomes, how big is this wavelength related either to the size of the particle or the trajectory of the particle? And so what we're going to find is for like ordinary particles or more massive particles, that this is not an important number to know. It just will almost look like a straight line for big particles. But for small particles like an electron, we're going to see that we get a wave-like description. And so, we're going to see this equation in action. It's probably not one you have to worry too much about solving problems with, but it's more of an idea that starts to get us into thinking that the electron, which is a particle, can it behave like a wave? Just like the light, which we tend not to think of as a particle, but does light have a particle property? And it does. So light is a wave, has a particle property, and then an electron is probably best thought of as being a particle that we'll see has a wave-like description. Now, another important sort of equation or idea comes from Heisenberg's work that showed that if you're trying to measure the momentum of a particle, at the same time you're trying to measure the position, that there's a fundamental limitation, that the uncertainty in position is x. So this is our uncertainty in position. So uncertainty in the position. And now what that means is, I like to think of this as you're firing an electron across a potential. So somewhere along this potential, you have an electron. And so somewhere along this point here, you have an electron. Let's say you want to measure it at this point here. And so that measurement would be x. So however long across the path where the electron's traveling is at the point you locate it, you call that x, and call this like 0, and call this 1 or whatever. This is like how far across that potential difference where the electron is being measured. And then the uncertainty in x is like the error bar is this. So this is our uncertainty in x here. It's sort of where the point's being measured versus the bar. So we go plus delta x on one side, and then on the other side of the particle is minus delta x. So we have x plus minus delta x. And this is the uncertainty in position. So it's like if you're measuring it to be like 0.1 meters across the potential, it's, well, what's the plus minus? If it's 0.1 meters, is it plus minus 0.01 meters? So 0.01 on one side, 0.01 on the other. So it's like the error bars. It's the plus delta x on the one side, minus delta x on the other, where the uncertainty is like the plus minus. And so for an example, if we're saying the position is 0.1 meters, and the uncertainty, the plus minus, let's say it's 0.01 meters. And so it's this uncertainty here that matters, not the actual position where it is. It's like, how precise do we want to be in the measurement? And you can imagine that the smaller this number becomes, the more precise we know it. So the smaller that number goes, the greater the precision that we know the position that was measured by. And so then we can relate that to the delta m times v, the uncertainty in the momentum of the particle. Well, the mass of the particle is usually a constant. It isn't changing. So we usually end up rewriting this as m delta v. So let me rewrite this as m delta v. Since the mass is usually a constant, and it's only its velocity that's then really being part of the measured quantity. So usually we're measuring a velocity here. The mass is a constant. And so we have some velocity that we measure, and it's the uncertainty in the velocity that factors into this equation here. And again, it's being smaller is actually more precise. So the smaller we make delta v, the more precise we know the velocity. And so it's the inherent nature of particles that we have this limitation. Now, we're going to find that the limitation for massive particles isn't such an issue. Like when we think of a baseball, we can watch a baseball, hopefully tonight. I see a hat in the back, so I know you're watching. Got to see probably more Cleveland shirts outnumbered. But so if you're watching like a baseball game, you can see the baseball being fired. And like we don't see it as a cloud. Sometimes in hockey, they did this every now and then where they tried to take the puck and almost make it like a long tail so you could see it better. That's the idea of almost the uncertainty principle. If you imagine when you fire the electron, you just see like a cloud moving and not a discrete particle. For an electron, a small moving fast particle, we're going to see that when you try to view it, it looks like a cloud as opposed to a distinct particle. Whereas if you think of more massive particles, they just travel like ordinary particles. So let's take a look at a couple equations. Now, I did these equations just written out because the actual doing the math isn't really the key detail here. The conclusion we can base off the results is, I think, what's more important. So the first problem, let me just move this here so we can try to look at the first problem first. So we're comparing what we call the de Broglie wavelength is the wavelength of matter. So the de Broglie wavelength is the one that's fitting to this equation here being solved from h over mv. And so we're comparing that for a baseball at 43 meters per second, which turns out to be a 95-mile-an-hour fastball, and then versus an electron that has a speed of 3.0 times 10 to the 6 meters per second, which for an electron is just like an average speed. So this, for a small, tiny electron, that turns out to be a very ordinary speed for it. The mass of the electron is given here in kilograms. And so when we go to plug in our math here, we're plugging in Planck's constant, joules times seconds, plugging in the mass of the particle in kilograms. Now we want to put this in kilograms just because the joule is a kilogram. So the 1 joule is equal to 1 kilogram meter squared per second squared. So when we think of what a joule is, it has the fundamental units in kilograms. So that's why we need to put the units in kilograms. For the mass, I mean, it was given to us in kilograms, so we want to keep it in kilograms. And then we plug in our joules times seconds. So we're canceling one of the units of S, the other unit from the meters per second, and then one of the meters squared cancels, leaving behind just the unit of meters. And so now let's try to interpret what it means for a baseball that's obviously pretty big to have a wavelength. So the wavelength is so small, it's times 10 to the minus 34 meters. That looks like the definition of straight line. You can think of how small is this wavelength to the actual trajectory of the baseball. It's inconsequential. So this is an inconsequential wavelength for the baseball. So this doesn't really mean the baseball behaves like a wave. That's just a straight line. So that's just defining what it means to be basically a straight line for the baseball. And so now if you think about the electron though, and calculate for the electron, which think about the diameter of an H atom is, the radius of an H atom is 0.75 angstrom, approximately. So the diameter of the atom is about 1.5 angstrom. And so if you think about the circumference times, pi times the diameter, be 1.5 times 3, around an H atom is about 5 or 6 angstrom. And so the trajectory around an electron for a single H atom would be on the order of angstrom times 10 to the minus 10 meters. And so then we go to calculate for the electron, we plug in joules times seconds for Planck's constant, put in our mass, really small here for the mass, but in units kilogram, and then meters per second for our speed of light, canceling out all of our units except for the meter. So we get 2.4 times 10 to the minus 10 meters, which converted over to angstrom. 1 angstrom, I don't know if we use the angstrom unit too much, but 1 angstrom is 10 to the minus 10 meter. So 2.4 times 10 to the minus 10 meters is 2.4 angstrom. And so now when we think of the circumference of the atom, this is on that order of the length around an atom. So this is a really important wavelength because it's on the order of the trajectory of the electron. It's on the order of the circumference of an atom. And so this is showing us that the electron behaves like a wave. So it behaves like a wave particle. So just kind of like light did. So the wave particle duality for the electron. Now, just because a particle behaves like a wave doesn't necessarily mean that we don't know anything about the wave. Let's think about the uncertainty principle, how it applies to then us leading to like the electron being like a cloud of uncertainty of where the electron actually is. And so let's compare the uncertainty in position So now we're throwing a baseball, and at some moment in time, we're, say, trying to determine the velocity of the baseball, and at the moment we measure the velocity, we're trying to know where is the baseball. How well can we see where the baseball is and measure the velocity simultaneously at the same time? And so that's where the uncertainty principle is coming into play. So it's a simultaneous measurement of the position and that velocity. Remember, we can rewrite this as delta x times m delta v greater than or equal to h over 4 pi. And so these are the two things that if we simultaneously measure them, we have a fundamental limitation given by the uncertainty principle that the uncertainty in those values must have a product taking into account the mass that's greater than or equal to h over 4 pi. And so the minimum uncertainty in position for the baseball, so plugging in h, so we're just doing the rearranging here to take that uncertainty in x would be h over, it has to be greater than or equal to h over 4 pi times the mass of the particle times the uncertainty in the velocity of the particle. So we have h over 4 pi m times delta v. And so then we plug in the mass of the baseball, and then we plug in the uncertainty. It's the plus minus that matters. And we don't have to like double it or anything. It's just whatever that plus minus is goes into the equation. That's our uncertainty in the velocity. So the v plus or minus delta v, it's the delta v that goes into the equation here. So we plug in 1 meters per second for the uncertainty for the baseball. And that gives us an uncertainty in meters on the order of 10 to the minus 34 meters. So we fire a baseball from the pitcher's hand to the catcher's mitt. We measure somewhere along the process at some position. The velocity is 95 miles an hour. Uncertainty in the velocity is 1 meters per second at that moment. We can be dead on pretty much on exactly where that baseball is. Our uncertainty in the position is really, really small, times 3.6 times 10 to the minus 34. We know exactly where that baseball is when we measure that velocity. So there's no issue here with the baseball, but what about the electron? So again, the electron, wavelength 2.4 angstrom, being fired, you can imagine being fired across a potential. You can imagine the electron spinning around an atom. But delta x, h over 4 pi m delta v for the electron here, we're just plugging in the mass of the electron. And then we're plugging in the uncertainty. It's the plus minus that matters. We're plugging in the 0.1 times 10 to the 6 for the delta v for the electron. And then what we get here is that it equals 5.8 times 10 to the minus 10 meters, which is equal to 6 angstrom. So we have really no idea where that electron is as it's spinning around the atom is the net conclusion. So you have an electron spinning around, say, an H atom spinning around that nucleus, and you know it's behaving like a wave from the Broglie wavelength with a wavelength that's on the order of the trajectory of the electron. And now we find we have no idea where the electron is. And so what that leads to is the idea that the best thing we can do for electrons is to describe like an idea that the electron for the H atom being like a spherical orbital just somewhere around the atom is what we think of as being the ground state of hydrogen. And then if we think of it being a little bit further away, that's n equals 2. Even further away, n equals 3. So this is going to lead us towards like quantum mechanics in a way, but a description where we're going to get from some solutions to quantum mechanics some quantum numbers to help us understand what different types of orbitals are possible. We'll get into what those orbitals look like. We won't do much with this equation, but that's the Schrodinger equation that gives us a better description of how the electrons are behaving in atoms by thinking of a probability distribution for the wavelength. So this is our wave function. The wave function squared is our probability distribution that we're seeing plotted here. That's our probability distribution. And I just want to finish with like maybe this slide here, where this is showing from n equals 1 to n equals 2 to n equals 3. We're just growing in size of the orbitals. That's kind of from a Bohr model. What we were seeing is this increase in size of orbitals. So the n value that we see from Bohr model is helpful because that's one of the 4 key quantum numbers for an atom. It's related to the size of the orbital. Then we have others that are related to shape of the orbital, and then others that are related to direction of the orbital or its orientation, and then also the spin. So we'll get into our 4 quantum numbers and things like the Pauli exclusion principle on Wednesday. All right, guys, thank you for being here, and I'll see you next time.